Okay, ready, Adam? Yep. Okay. Okay, hello everyone. I'm going to be talking about projections and simulation of Arctic and Antarctic sea ice in the latest general circulation and Earth system models. I'd just like to, before I start, just say that this work is part of my recently completed PhD work at the University of Reading. And I'd like to acknowledge David Ferrer and Danny Felton for their supervision. So plots I'm showing on this slide, being something similar already today. This is showing projections of Arctic on the left and Antarctic on the right, sea ice extent in CMIP6 models. So the lines here are ensemble means, and the shading is just a standard deviation to give an indication of the spread across both models and their ensemble members. So, and this is shown for a range of different future emission scenarios. So what you can see here is that these ribbons are quite large. Even by the time we get to year 2100, there's a substantial overlap of different scenarios. You can also see on this figure that there are substantial systematic biases relative to observation. So this kind of is a sort of widely acknowledged problem, and it is something which hinders confidence in our ability to assess the future climates. So one thing that we would like to use climate models for, just as an example, is this. Is it because it's lost focus? There you go. All right, got it. Thank you. Yep. So one question that we might like to ask is, when will the Arctic become seasonally ice-free? When will the summer ice be lost? And again, this is something that we saw earlier on, but here's another way of looking at it. So here is a list of CMIP6 models. It's not all of them, it's just a sample. And this chart here is just showing the time where they first show the September sea ice extent to be below that 1 million square kilometer threshold. And it shows the ensemble range of each model. So you can see just by having a quick look at the range of times there that you have some 50-year range there. An outlier model here which still shows substantial sea ice at the end of the next century. Of course, this is just one scenario as well. We can look at the other scenarios, which just muddies the waters even further. You see a very wide difference in how different models have much larger internal variability, such as length of each bar. And overall, we are sort of struggling to get a clear picture from this. And it means that some researchers have used model selection criteria to try and narrow down these estimates. So this kind of spread here implies substantial differences in the mean states and rates of change of sea ice cover in the Arctic. And so we would like to be able to understand what are the drivers of this. So as alluded to by the title of my talk, we kind of have a hypothesis that the ocean may be playing a significant role here. So there's a lot of existing literature on this topic, on the relationship between the ocean heat transport and sea ice in coupled models. So, for example, if you just take the control simulations of these models and you look at the multi-decadal variability, and see the unforced, they're just free-running models, free-running simulations. And if you just plot anomalies in sea ice area, so total sea ice area, which is on the vertical axis there for each hemisphere, and if you do a scatter plot of that against the total heat transported by the ocean at the same time scales, you can see this clear relationship between the two quantities, where when you tend to have more heat being transported towards the poles, you tend to have less sea ice. So many studies have focused on kind of the mechanisms behind how this works. And I'll just shamelessly plug our own earlier work here, where there are many other examples. This is one where we actually looked at this multi-decadal variability in the control simulations, and we actually identified that despite this kind of similar relationship in the two hemispheres, there are actually substantially different pathways with which the ocean heat is actually affecting sea ice cover. But we are still the jury is still a bit out on how this relationship is relevant to future climate simulations and the uncertainty that I was talking about earlier. So I'm going to try and address two key questions here. One is, what is the relationship between the changes in ocean heat transport in these models in the context of historical and future simulations? And we're also going to address something which has not been given much attention, which is what is actually setting this apparent sensitivity of changes in sea ice to changes in ocean heat transport, which you see in models. So I'm going to essentially show one figure for the rest of this talk, and I'm going to build it up very slowly because there's a lot of information there. So we're going to start off very simply, and we're going to be looking at first changes in the sea ice and polar temperature over the satellite era. That's just so we can compare to observations, and then we will extend it to the future simulations later on. So here is a plot. On the vertical axis, I'm going to explain what these quantities mean. On the vertical axis, we are plotting change in sea ice. On the horizontal, we are just plotting change in polar surface temperature. Each one of these points is a different model simulation. There's about 15 models in total, and we include all ensemble members together. Now, the way we are defining these quantities is a bit non-conventional, but there's a very good reason for it, which will become clear. So let me just explain schematically what I'm doing. So I've said on the vertical axis there, sea ice edge change. So what we are actually doing is we're not using sea ice area or sea ice extent. If this was an example of what our sea ice cover looked like in a model, we are computing the zonal average ice edge latitude. And this may seem a bit strange, especially when you look at this diagram and see that the sea ice cover is not really lining up along a latitude circle. And it will become very clear why we are doing this later. And it turns out that when you calculate this quantity, it's actually directly proportional to the sea ice area anyway, just with a change of sign, because obviously when there's less sea ice, this latitude will increase. So these points are all increasing. That means more sea ice and less sea ice, or stronger decline. For the horizontal axis, we are computing the average air temperature over a spherical cap. So we're just picking some fixed reference latitude, it's about 65 north. Our results are relatively insensitive to this. So what this plot is simply showing is that when simulations tend to have a stronger change in surface air temperature, that pink region, over this time period, and I should also probably have noted that we are, when I talk about a change here, we are dividing our time period up into two 21-year climatologies. So we are looking at one climatological average to the next. And so this is simply saying that the simulations which show a larger warming also show more sea ice loss. This is pretty straightforward. We can do something similar for the Southern Ocean as well. So just imagine flipping the diagram upside down. We do the same thing, and we find the same basic relationship. So just again, just to be absolutely clear, when the south polar temperature warms faster in these models, the change in sea ice cover is stronger because this is in degrees south. Okay, so we'll just, so I'm just going to put some observations on here just because we would like to put this in context of the real world. This is one of the reasons we start with surface temperature, because we can actually do this comparison. So I've just used a few atmospheric reanalyses there to look at the change in surface temperature in both hemispheres. That's the colored lines. And then we've just used satellite sea ice concentration for the sea ice change. And so here again, you see this problem of model spread, right? Because the actual range of all the CMIP6 simulations was actually about 5 or 6 times the observational uncertainty in the sea ice change. You also see, although it's not hugely obvious from this one, you do see a slight tendency of models which are getting the sea ice decline about right, be doing so on the kind of warmer end of the atmospheric reanalyses in the Arctic. And again, as for the Southern Ocean, well, most models are completely off of observations. So I talked about ocean heat transport at the beginning, and that's not on this plot yet. What we're going to do is we're now going to compute the ocean heat transport change over this time period in all these model simulations. And so by ocean heat transport, I just mean the total heat transport by the ocean integrated into the region that we are considering. So I'm now going to add that to this plot, and I'm going to do that by coloring in all the points according to the value of the change in ocean heat transport. So when we do that, the points which are more red are showing increases in ocean heat transport over this time period, and the blue are showing decreases. So you see that in the Arctic, models which are showing an increase, those are the red points on this end, are the ones which have greater polar warming and stronger sea ice loss, and vice versa. In the Southern Ocean, it's the same kind of thing. You see this pattern of blue to red going up the plot. I think it's interesting to note at this stage already that if you look at the points which are closest to the observational estimates, those are the ones which tend to have almost sort of close to zero change in ocean heat transport in the Northern Hemisphere. Whereas in the Southern Ocean, it's the simulations which tend to have a decrease in net heat transport which get closer. So this is kind of all quite intuitive. More heat, it's warmer, there's less sea ice. This all kind of makes sense. But what we don't have any explanation for is why we have this strong correlation of these three variables. So that's what we're going to do now. So yeah, why do these relationships occur? So if we come back to our simple schematic and think about what we've plotted here, if we just extend this diagram a little bit more, then we can create some tools to explain the relationship between these quantities. So we talked about the ocean heat transport into our polar region, but of course the ocean is not the only thing which brings heat into the Arctic. We also have to consider the atmosphere. So we'll add atmospheric heat transport onto there at the same latitudes. And to sort of complete the description of this, the simplest way we can do that is just to construct a few heat fluxes. So if we're thinking about large scale climate on long time scales, which is what we're doing here, then all we really need to think about is the fact that this region is driven by shortwave radiation, so net shortwave. It cools via long wave radiation to space. And then we have to consider also the fact that there's a surface flux of heat between the ocean or sea ice and the atmosphere. So what we've now essentially drawn is a three-dimensional view of an energy balance model, like what Ian was describing in his talk. So if we take one final simplifying step and zonally average this picture, then there we are. This is a zonal average energy balance model, the likes of which Ian was talking about. So in our case, this is all the detail we need to explain the plot that we had before. Okay, we don't need to worry about how the OHT is defined or the AHT. But what we now have is a framework by which we can link these heat fluxes together. So if we just think about energy conservation, then we can write down this equation. So this is simply saying net heat into the system, which is the short wave, the yellow arrow, the two heat transports across our reference latitude. And if we're thinking about changes in the system on long time scales, that must be balanced out by the heat out of the system, which is affected by the long wave radiation. So we have an equation. It has OHT, it has 3 other things which we're not interested in, and it doesn't have surface temperature or sea ice in it. So all we need to do is figure out a way of rewriting the other terms, which I'm not going to go over all the details of that because, well, it's not too interesting, but I'll just explain very briefly how we do this for a couple of them. So sea ice enters in. So you see, this is why we used the ice edge latitude earlier, because we are now considering a zonal average system. If you take some climate model data or even observations, actually this would work as well, and you just plot, this is much like the plot I showed at the beginning here with multi-decadal variations in OHT and sea ice. Now I'm showing multi-decadal variations in sea ice and net shortwave radiation, which you see you get a straight line, which allows us to rewrite the shortwave term in our equation with sea ice. We can do something similar for the AHT term. So this one is this is a very well-known phenomenon in climate models, where when you tend to have anomalous ocean heat transport, the atmospheric thank you. Yeah, so basically we derive a few simple approximations, which allows us to rewrite our energy conservation equation. And ultimately we end up with something which looks like this. So you'll remember hopefully that we had a plot where I was plotting changes in ocean heat transport, polar surface temperature, and the zonal average ice edge latitude. And we have now derived a simple linear equation which relates those quantities together. And so the K1 and K2 here are collections of parameters which we have found can be suitably treated as constants. So this is the plot that we had from earlier. There's our 3 quantities, delta TS, delta OHT in the color, and then delta sea ice on the vertical. We calculated the value of K1 and K2 separately for each hemisphere. And then we used our equation to see how well it captures this relationship seen in the models. And so when we do that, we add it to our plots, that's the EBM line on here, you can see that this line very well captures the emergent multimodal relationship between changes in sea ice, surface temperature, and ocean heat transport. We can extend this now to the future period. So we're now going to basically do the exact same thing, but we're just going to extend our time period into the mid-21st century using a this is mid to high emission scenario. So now it's basically the same thing, but I've plotted it against the OHT change. The surface temperature change is now hidden, and I've chosen to reveal model identities. So I think this plot is quite interesting because it shows that if we look at the Arctic here, you can see there are some models which are showing almost no change in sea ice cover over this time period, whereas there are some models which are showing 10 degrees of latitude change. And again, that is, you can think of that in terms of the actual sea ice area as well. And that model, which shows almost no sea ice change in an experiment which is meant to be, it's the same climate change simulation, it is doing so with the largest reduction in poleward ocean heat transport. And given the effectiveness of fitting our data with the energy balance model in green there, this is entirely understandable as a constraint on large-scale energy conservation, which is what we started with in our equation. One other point which I think is interesting here is that in the northern hemisphere, you do see like individual models are separated, whereas there is a lot more overlap of models in the Southern Ocean, which may reflect a stronger role of internal variability in the Southern Ocean and model biases in the Arctic. So I'm going to leave it there with my key message. There is a lot of existing evidence, in addition to what I've shown here today, that there is a strong relationship between the simulated ocean heat transport and sea ice changes in latest model simulations. And this relationship with the energy balance model provides an effective collapse of that data onto a very simple system, which provides, I think, convincing evidence that the ocean is a key driver, potentially, but obviously there's open questions with this, a potential key driver of model uncertainty in future projections. Yeah, I think I'll stop there. Thank you.
Okay, thank you, Jake. Do we have any questions? Yeah.
Yeah, I really enjoyed your talk. I had a quick question about how you did your energy balance model there, the terms that were added together. So the right there's no ocean heat uptake, right? And it's I guess the next slide. And this is a transient runs you're looking at. My recollection is that typically in these runs, there's sufficient ocean heat uptake that even though there's an increase in meridional heat transport into the polar region, the surface of the Arctic Ocean is actually taking heat, the heat's flowing downward at the surface, into the surface, and that's all getting balanced by the warming of the Arctic Ocean. So I was just wondering how that might affect the story if you add on that next slide, I guess, a term for the ocean heat uptake that gets added to, it's not that one, okay, sorry, maybe the previous two slides back. There we go. That gets added to that relationship, right? A fifth term.
So a couple of things, I guess. So one thing is that we are looking at quite long time averages. So we chose 21 years here. I mean, it's still obviously, it's obviously it's like a transient climatology, if you like. But I think that the initial equation is still correct, right? I mean, I think what you're guessing at is more. Yeah, go on. Well, it would be in. I don't think so. Yeah, maybe. Yeah. Well, I mean, maybe it works, right? Yeah.
I think Jake did look at the heat content change of the ocean. Okay, and it was just small compared to the other terms. So he's not showing it here, but it is in his work. I'm guessing Jake could show you that in elaborate detail.
Okay, do we have any more questions? Perhaps time for one or two more. Okay. Oh, yeah.
Thank you. I find this very convincing, but I think it comes a little bit at odds with the work of Pith and Moritzen, where they looked at the warming contributions to polar amplification, and they came to the conclusion that ocean heat transport wasn't a factor. And I wonder if it's a matter of the latitude that at which you define the heat transport across. Do you have a
Yeah,
sense?
so here we're using 65 north and 65 south. We have tried different latitude, and we find that it works just as well. If you go, too far south, obviously it won't. When you're too much equatorward, it won't work. It's more of a problem in the Southern Ocean. I don't know if the work that you're referring to is Arctic specifically. Was it there? Oh, okay. There's more of a sensitivity to the reference latitude in the Southern Ocean. In the Arctic, it works, I think, between about 50 and 70. When we do this analysis.
Hi, Cecilia. I wasn't really sure what you were saying, but one thing which I think Jake showed a picture of it, okay, is that there are pathways by which the ocean heat finds its way to the sea ice, okay, and one of them is via the atmosphere. So depending on precisely where you're measuring and how you're assessing it, okay, you may say it's to the atmosphere, whereas we would, or Jake would argue that actually what's happened is the ocean is losing its heat to the atmosphere, which is then being redistributed over the ice. That could be part of the answer.
Yeah, maybe if we could continue conversations. I think we're heading into the coffee break now, so perhaps I'm sure Jake will happy to answer further questions then. But yeah, if we the next session will start at 4. I think we've got one more talk and then followed by a discussion. So if you have any questions, thoughts to discuss then as well. But otherwise, yeah, we will gather again at 4. Okay, thank you. And thank you again, Jake.
Rechargeables aren't very recharging.